Hello, and welcome back to Stat 3050 at the University of Wyoming. We are online, but we're having a good time. It's pretty good. So before we move on to more complicated models in regression, I kind of want to talk about R-squared just a little bit because it's frequently misinterpreted, and I want to kind of nip that in the bud before we go on. So let's talk about it. Well, what is R-squared? R-squared is sort of this overcomplicated definition. Okay, so what is R-squared? Well, R-squared frequently is sort of overcomplicated as far as the definition goes, but simply we can look at it as the percentage of the outcomes variance that's explained by the predictor. Sometimes we have one predictor, sometimes we have multiple predictors, but really it's just saying, how well is X doing at defining Y, or at least predicting the behavior of Y. And frequently, R-squared is called this coefficient of determination. So we'll see a little bit more about that in just a second. But the sort of simple formula for R-squared is this 1 minus the explained variance divided by the total variance. So we'll see a little bit more about that here in just a second. So on the left over here, we have this R-squared of 0.81. So we would say that about 81% of the variance of Y is being explained by X, or 81% of Y is being explained by X. In this case, it's this temperature and revenue. So we've got that, and we see over here the other end of the spectrum. About 24% of the variance of Y is being explained by our one predictor here. And it just so happens that as that number increases, the points get kind of closer to the line, right? We see that the points fit around a line a little bit better. That doesn't necessarily mean that it's a good fit, but it's just something that kind of happens, right? And we see with the lower R-squared, we see that these data points are a little bit more spread out across the line. So that's all right. This next slide, I'm going to give you a second just to pause the video and take a look at it and just kind of get a better idea of what's going on. Nothing, crazy important here, but just sort of some kind of recap maybe on older intro stat classes when it's been a while. So just take a look at it and sort of review real quick before we move on. So what do we mean when determination does not equal correlation? Well, we mean that R-squared does not equal R. Okay, well, so what is R? This is the symbol for correlation. This is not the programming language. So the coefficient of correlation, this R, ranges from -1 to 1, right? And we know that when something is a positive 1, something has a positive correlation, it looks something like this. The two variables move in unison, okay? And then when the correlation is negative, we see that they move in opposition to each other. So as one goes up, the other one goes down. And then a correlation is 0 would look something like this, right? Where there is no correlation between the two variables that we have. So that's all right. When we're looking at R-squared, this determination coefficient, this coefficient of determination, we see that it only ranges from 0 to 1. And it's most of the time, it's kind of put on this percentage thing. So 0% to 100%, like that. And we know, you can kind of see here, that when R-squared equals 1, we see that it would be something like this, right? It'd be something like this, where each point falls perfectly on the line. And it could be either. It could be this way, too. It could be this way, right? Very interesting, right? And so we would just say that X perfectly explains Y, which is great, right? Oftentimes, that's never ever going to be the case. Your R-squared should really never be exactly 1. Something's gone wrong if it is. And then we'll talk about that more in just a second. And then an R-squared of 0, none of X predicts Y. None of Y's variance is being explained by our chosen predictor. And oftentimes people sort of say, oh, okay, well, if your R squared is high, that means you have a good fit model, right? Well, not necessarily. So let's take a look. When we say we have a low R squared, that means that X is not doing a great job at explaining Y on this sort of linear scale, here. However, we see that there is a big correlation between these two data points, right? Between these two variables, I should say. And so we see, okay, well, they are highly correlated, just not in a linear fashion. It's got this sort of like parabolic sort of behavior to it. So this line that we've calculated right here, that we've constructed, it's totally legit. However, it's not maybe the best way of modeling these data. So we would have a low R squared, but the R itself would be high if we were to model it like this. And then the R squared would change too if we changed the line to fit that curvature. And then we'll move on to fitness, goodness of fit, I should say. So we have this high R squared here. We can see that in this model output. For those of you who are curious, this is a Minitab output. That's just another programming language. Sorry, not a language, more or less a statistical software, point and click kind of thing. Some classes here use it, some classes don't. That's okay. But we see here that this line is doing an okay job, right, of fitting, I think, right? Well, it turns out that when we look at the residuals, we see some major curvature, right? Some major curvature. We're still modeling. We can take a look at the regression equation here, and we see that it looks something like this. It looks something like this. Beta 1x plus beta 2x squared plus beta 3x cubed. Good Lord, right? So very overcomplicated, but we're still modeling it in this way. And we see that there's major curvature, right? It's really not doing that good of a job. But it turns out that our R squared is super high, right? So it's not necessarily the best indicator of a good fit, right? It's not a good indicator. So that's why we always check the R squared and then the residuals. Always look at the residuals, because oftentimes the residuals tell you more information than just this one thing being estimated here. Okay, so we sort of have this idea of overfitting, right? This is not a great model because of many reasons. It's complicated, the residuals don't look good, but the R squared is high, but that doesn't mean anything now, right? We know that the residuals need to be good. They need to meet our 3 assumptions before we can say anything about the model. Well, so let's talk a little bit about R squared, the adjusted R squared, and this idea of overfitting. Okay, so what does R squared adjusted do? Well, R squared adjusted, we've kind of seen it before, but it takes into account sample size and the number of predictors that you're including in your model. And so that could be a bunch of different predictors. That could be, let's say that you're looking at height and you want to look at as a function of, weight, like income, and like coordinates of where you live, right? 3 things that are just all over the place, right? But the R squared would still be higher than a model with just 2 predictors in it. So let me actually draw that out. So let's just say that you have some outcome, and you have beta naught, and then beta 1, x, and then we'll call this x1, and then beta 2, x2. And let's say that these represent 2 different measures. This R squared would be lower than, a model with the same stuff, plus another predictor. Okay, so the R squared is higher because we've added a new thing. We've added a new variable. So that's oftentimes always true, but often not great, right? It's not great. So we have this idea of adjusting the R squared for that kind of stuff. And that does a fairly decent job. That does a fairly decent job at adjusting for sample size and for the number of variables that we have. And often it tells you if you're overfitting your model. So let's just say, sort of what I've got right here, if there's a big jump, if R squared goes, and it's a huge jump to the adjusted r squared, that is sort of an indicator of overfitting, Right, so if something happens, bring this example down here just for a second. Let's say that our r squared was, let's say that we have this huge, really complicated model. I can write it up here where the intercept is this, and we have this, and it goes all the way out, to, we'll say, 50, right? We have 50 predictors in this thing. Let's say that our r squared, it would probably be something super stupid high, right? 99.9. Okay, well then the adjusted r squared, would look something like this. Right? Maybe not that big of a jump, but still something along those lines, right? This is an issue. This is an issue of overfitting that we would need to kind of remedy by looking at our model and saying, okay, well, maybe we should take out 47 of these predictors. Who knows? So let's take another look at it, right? So we can either add a bunch of predictors, or we can really overcomplicate the model, okay? By adding these sort of different square terms or cubic terms or whatever. So this over here on the left, this is a fairly simple, this is just data I've made up. But this is our normal, beta plus mx, b plus mx, or this, our beta plus beta 1 x1, right? That kind of situation. Same thing, and we get an r squared of about 0.3, right? So 30% of y's variance is being explained by x, which is decent. For one single variable, it's you can't really ask for more. Okay, and so this is good, right? This is a fine model, right? Without looking at the residuals and such. Well, let's move over here. Let's move over to the right. When we make this really complicated function, this function is still legitimate. We've traced together all of the points, made this perfect function that perfectly explains x and y, perfectly explains y by x, right? But what is the model? Can you explain that to me? I have no idea. I have no clue, right? Be this something that was very complicated mathematically, right? But our r squared is 1. Our r squared is x perfectly explains y. Well, what happens if I take the same model, and then, add a new data point? Oh boy. Well, I just kind of mucked everything up, right? We don't know where this line is anymore. We don't know how this function is going to work now. So it's really not great, right? So having a really overcomplicated model like this, right, sort of like this whole thing here, is really bad because, well, you've perfectly fit your model to the data, but the moment that you add a new data point in, your whole model is trash, right? Plenty of ways to avoid that. That's why we use regression like this with this straight line. It's simple. It's good, right? We are able to say there's still some error component to it. These residuals are sort of an error component. But for the most part, it's fine. It's totally okay. This model that we have on the right here, this is no good, right? It's too complicated. We can't explain anything. It's just not, it's not very intuitive. It's not great. So we kind of move on, and then we're just sort of recapping here, because I want this to be relatively quick. First knowing that r and r squared are not necessarily the same thing. Oftentimes they're related, but we can kind of see that correlation, at least in the English sense, maybe not so much in the statistical sense, correlation does not necessarily mean that x is doing a great job at explaining y. And we kind of saw that when we saw data that looked like this, right? Okay. Using r squared and the residuals in your judgment. Always do that, right? Put a lot of value on the residual plots and analyzing the residuals. So oftentimes, you can have a high r squared, and sometimes it's a good fit, but not always, right? Not always. We saw that in that second example there. So just kind of keeping that in mind. Okay, and then we move on to our third, and when we say that we don't want to add redundant variables, well, what do I mean by that? Well, let's say that we're looking at air temperature in Celsius, right? And we include all these different models. We include all of these different variables, length of day and the season, right? And then blah, 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 some other stuff. And then let's say, well, we actually record the air temperature in Fahrenheit too. That's going to look something like this. You'll get an r squared perfectly of 1 because these two are doing the same thing, right? If you were to just plot these two temperatures, you would get some plot that looks like this. In real life, we know that they're doing the same thing, right? They're doing the same thing. They're telling you the same information. So getting rid of this, right, would definitely help your model out and give you a better picture of what's actually going on. And then, lastly, simpler is better. You want to leave room for error. You want to leave room for error. It's very important, right? Having sort of this over-underestimation of things being there, just so we know, what the limitations of our data and of our model is. In this case, overcomplicating the model, if we were to come back over here, and I'll try to do this delicately, if I were to do that, if I were to trace together all of these lines, I've got this perfect model that perfectly explains why, right? But one, it's very complicated, and then two, it's very sensitive to new data, right? So if I were to put some new data point right there, this whole thing is whack, right? It's not good. So just sort of keeping that in mind, that you don't want to be too complicated with your models. Of course, plenty of other resources online in your textbook, R for data science, all that. If you have more questions about it, feel free to ask. Feel free to reach out, and I will gladly help you out. Alrighty, I will see you next time.